Hello, in this video I'm going to talk about random number generation. There's some interesting topics to be explored here because computers really can't generate random numbers. So they're designed to be 100% predictable. So how do we get them to generate random numbers? There's some interesting technical material here. So imagine that, put yourself back long ago when people were trying to make games that appeared to take place in a large universe. I've got galaxy with 255 different planets, or I've got a side scroller or a vertical scroller that is producing kind of an endless amount of terrain coming at me. But every time I play the game, I get the same terrain. It's like there's a huge database that stores the world, but I know in the back of my head that there's no possible way they can be storing all of this because there just isn't enough room on the disk or cartridge or tape or whatever. So how do you generate the same thing every time without having to store it? And that's where we get into random numbers. River Raid, the classic killer app of the early 80s by Carol Shaw. If you play a game like this, every time you plug in that cartridge and start the game, the terrain configuration is the same when you fly down that river. And eventually you start wondering, if this cartridge only has 4K on it, how is it possible that it's storing all that terrain? And the answer is it isn't. It's generating it procedurally using random numbers. So computers can't actually generate random numbers. They can generate what appear to be random numbers. We call them pseudo-random numbers. They're numbers that at first glance look to have no pattern. However, if you kind of know under the hood how they work, then yeah, there is a pattern. It's just that we don't see the pattern. They're random enough is what a pseudo-random number is. They're fake random numbers. They're good enough. One kind of not so, or one famous way of generating random numbers, and I say random in quotation marks, is the Fibonacci sequence, where you take two numbers and you add them together to get a new number. And then you add that new number with the previous number to get a new number, and you just repeat that to generate a series of numbers. So the rule for Fibonacci numbers is each number in the sequence is the sum of the previous two numbers. So it's real easy to understand if you look at it. So if I start with the numbers 1 and 1, I add them to get 1 and 2. So then now I have 1, 1, and 2, and I take the 1 and the 2 and I add them to get the 3, and then the 3 and the 2 together to get the 5. And you can see that I go up in this very predictable way. This is a Fibonacci sequence right here. I don't have to start with 1 and 1. I mean, the official kind of textbook version starts with 1 and 1, but I could start with different numbers and I get a different series of numbers out of there. And that's what we're talking about then, is seeding the random number generator. The seeds are kind of what I plant into the random number to have it grow a different series of numbers as it executes its algorithm. Now, if I were trying to use this to generate numbers between 1 and 10 or something, so I'd generate the Fibonacci sequence, and I'd take every number and I'd divide it by 10 and take the remainder, then you might see that the first few were the Fibonacci numbers, but after that it would become kind of hard to tell that you were dealing with a Fibonacci sequence under the hood. However, the Fibonacci sequence does not really generate you a great distribution of random numbers. You tend to start seeing patterns, visual patterns in your game if you're using it to generate boards. So we're going to look at a different way to generate random numbers. The Fibonacci sequence also has this cool side effect that if you take the numbers it generates and use them to make squares and kind of tack the new squares onto the previous squares at right, going counterclockwise, you will end up with one of these cool Fibonacci spirals that shows up in nature. It's been mathematically proven it's the most effective way to pack seeds onto a cone like we have there on the right. I don't know, it's just pretty cool. It's been used to explain all sorts of patterns in nature. And again, like I just already mentioned it, if we wanted a different string of numbers out of our Fibonacci generator, well, we would just start with, instead of 1 and 1, we'd start with 10 and 99, or just two different numbers, and we would get a different series out of that formula. All right, so let's keep going on. So the next algorithm we're going to talk about, though, a better way to generate random numbers, is called the linear shift algorithm. And in order to talk about that, we have to provide a definition for a term, and that is exclusive OR. When you exclusive OR two things together, it's a binary operation, so it only applies to ones and zeros. And if you XOR them together, you get a 1 as your output if one and only one of the inputs was a 1. So if one operand exclusively is a 1, you get a 1. Otherwise, you get a 0. And if that's confusing, here it is as a table, as a truth table. So here's all the possible combinations of operand 1 and operand 2. Notice I'm just counting up in binary here. It'll list out all the numbers, 0, 0. This is 0, 1, 2, 3. And then this is the result if we XOR them together. 0 XOR 0 is 0. 0 XOR 1 is 1, because exclusively one of the operands is a 1. And for the next pair, exclusively one of the operands here is a 1. So so that's a 1. And then the 1 and 1, if we XOR them together, we get a 0. Because according to our formula, only one of the operands can be a 0. 1 XOR 1 produces a 0 as the output. A regular OR would give you a 1 as an output, which, I don't know, kind of, am I wearing a left shoe or am I wearing a right shoe? Well, the answer is yes, I'm wearing both, right? That's the regular OR operation. Here we say, okay, if you're wearing one shoe and only one shoe, then the output is a 1. But if you take two 1s and you XOR them together, you get a 0 as the result, because both operands are the same, and to get a 1 out, only one of the operands, exclusively one of the operands, has to be 1. All right, so now that we understand XOR, we can talk about the linear shift algorithm. It sounds scary, it sounds super technical, but it's actually very easy to understand. Linear shift just means we take things and we just slide them down. We're shifting things in a line. That's what we're going to do to generate random numbers. So imagine I have a number here, which is really just like, an array of bits. How could we generate random numbers using these numbers and shifting them around? Well, that's what we're going to look at. So here's the formula for linear shift. We're going to take two bits. Doesn't matter which bits. We're going to call those are called the taps. That's the technical term for them. And we're going to take those bits and XOR them together to get a new bit. Then we're going to take all of the bits in our number and we're just going to shift the number down by one position. So the bit that's on the right is going to fall off. In binary, this is a division by 2. That just shifts everything to the right. But there are also operations. There are also instructions, opcodes for doing left and right shifts. And there's actually different types. There's all different types of shifts. But we're gonna do a shift to the right, and we don't really care what happens to that bit on the left when we do our shift, because we're going to overwrite it in the next step. But the first step is to take two bits called the taps, XOR them together to create a new bit. Then we tell all the bits to move down, and then lastly we take that new bit and stick it on the far left where there's a vacancy now because everybody moved to the right. And let's look at this as a picture, just kind of watch it go here. So here's our algorithm. We're going to use bits 0 and 2 as the tap. So bit 0 is the one on the far right. That's just kind of, I don't know, down at the bit, down in the weeds at the bit level. That's how things are numbered. But it doesn't matter as long as you can see the arrows. So we're going to take those, the two bits with the arrows under them. Those are our taps. We're going to take those out, XOR them together to get our new bit. So 1 XOR 1 is a 0 because they both are the same value. In order to get a 1 out, only 1 can be a 1. So the new bit was a 0. And I'm just going to store that down there at the bottom left. And then I'm going to do my linear shift. I'm going to take everybody and say move to the right. So I shifted everybody to the right, and now I've got a vacancy on the left, and now I'm going to take my bit the new bit I generated, I'm going to stick it there on the left. And now I've generated a new number, and that's it. I've taken one number and used a formula to turn it into another number. And this is mathematically proven to cycle through all the possible values with one caveat that I'll show you later. All right, well, let's just do it again, just for the sake of repetition, just to make sure we've got this. So let's repeat. So we're going to pull out two new numbers. That's the same taps, right? And I'm going to get a 0 and a 0. XOR those together, I get 0. That's my temporary value. Now I'm going to tell everybody to shift down to the right. And now I'm going to take that 0 and I'm going to stick it on the left. And I've taken one number and I've used my formula to turn it into another number. And then let's do it one more time for good measure. I'm going to pull out my taps, and we're going to get a different result this time because now you understand XOR and you're like, oh, I see where this is going. So my taps are a 0 and a 1. I XOR those together. I get a 1, and that's my new bit. Now I do my shift, and I take my temporary value, the result of the taps, XORing the taps, and I stick it in on the left there. And now I've generated a new number. So this will cycle through all the random numbers in a way that will give you kind of a better distribution of numbers than a Fibonacci style random number generator, with one caveat that I'm going to talk about here. So the problem is, if we start with 0 as our number, a random number seed, 0 XOR 0 can only generate 0, and we will just end up with it will never end up with anything other than zeros in our random number generator. So you can't start with 0 as your seed. And if people want numbers between, say, 0 and 10 or something, well, then you really just have to generate numbers. You generate the numbers the same way, but then you subtract 1 off of whatever comes out of the random number generator. So that's just, if you're actually trying to do this, you just have to be aware of the fact that when you seed your random number generator, if you are using, well, if you're not using specific numbers, you're getting your numbers from somewhere else. You have to make sure that those numbers are not 0. Now, where would you get those numbers from somewhere else? That's what I talk about. That's what I'm going to talk about now. So let's go back to River Raid, though, and talk about flying down that river. And every time we start up that game, the terrain comes at us, and it's the same terrain every time. Well, is this using linear shift to generate its, to generate the terrain on the fly? And it turns out the answer is yes. So here's an interview I found with Carol Shaw, the author of River Raid, and in here, if you dig around, she says that she's got to cram all this terrain into just 4 kilobytes of ROM, which is impossible. So it says, I used a pseudo-random number generator to decide what the next width was going to be. That's the width of the terrain, or the width of the river. So basically, you do a couple of shifts and an add or something and generate the next pseudo-random number, and that decides what the next part of the river is going to look like. So there we go. There's the linear shift algorithm. And then she says in the next answer, yeah, basically, if you start with the same seed every time you play the game, it will look the same. So she's talking about using the linear shift algorithm with a specific seed. And what they would do when they made these games is they would try various seeds and see, okay, like does the terrain start off easy and get harder, or is it too hard from the start? And they would play with the seed to have the kind of the terrain that got generated kind of increase in difficulty. So there was some design there, even though the terrain is baked in. They have to figure out which seeds produce the best terrain from the standpoint of playability. And seeds haven't gone anywhere. In Minecraft, right, if you want to generate terrain off of a particular seed, yes, absolutely you can. But the interesting thing is, so you can either start with a seed and then have predictable terrain, but if you really want random numbers, well, then you need some sort of randomly generated seed, and you've got some chicken and egg problem here. How do you get around that? Well, you can use the clock. So seed your random number generator with some time value, because the time will be different every time you play the game. That will work. And but what if you're on something that doesn't have a real-time clock? You're on an old computer, an old console, some embedded system that doesn't have a real-time clock. Well, like on an Arduino, you can read a serial port when the thing starts up, and there'll be a garbage value, and you can use that as your random number generator seed. But there's an even more elegant way, and that's this. You have just some screen when the thing starts up, and you say, press any key to continue. Like, why? I don't know. We're just so used to seeing this, we don't even think about it. But really what's going on here when you do one of these screens is the program is keeping a counter, waiting for you to press a key, and then when you press the key, it uses that counter value as the seed for the random number generator. So there's tricks like that. If you know your hardware, you can sometimes get some random numbers out of the operating system's data, if you're on a system where there's no memory protection. So there's different ways of getting random number seeds, but you have to think about what do I want out of my random number generators? Do I want predictable randomness, or do I want random randomness? So you can either start with a seed or you can generate your own seed using the clock or some other values that way. So that's kind of the background on random numbers I wanted to convey, because we're going to actually go make a linear shift random number generator in C Sharp. And if you understand how it works, then you'll get more out of building the actual activity. So I thought that was hope that was somehow enlightening, and I hope you enjoy building your random number generator.